created by MindSticks Foundation Trust. Hello, students, and a very, very warm welcome to our final session on Chapter 2. I'm absolutely thrilled to have you all here today. We're going to wrap up our fascinating journey through the periodic classification of elements with Part 3 of our explainer. So get your notebooks ready, sit up nice and straight, and let's dive right in with our full concentration. Here's a quick look at our agenda for today. We've got 5 key things to cover. First, we'll explore trends in atomic size. Then, we'll define metallic and non-metallic character. After that, we'll uncover the actual underlying causes of these trends. We'll also look closely at a couple of specific chemical families. And finally, the fun part, we'll solve some chapter exercises together. All right, let's jump straight into Section 1, Trends in Atomic Size. We all know that size, or volume, is a really fundamental property of matter, right? But how on earth do we measure an atom when it's so incredibly tiny?
Well, we measure it using something called the atomic radius. Now, please jot this definition down clearly in your notes. Atomic radius is simply the distance between the center of the nucleus of an atom and its very outermost electron shell. And because atoms are literally microscopic, we obviously can't use meters or even nanometers. We have to express this in a unit called the picometer, which we write with a small p and a small m. Just to give you an idea of the sheer scale we're talking about here, 1 picometer is equal to 10 to the power of minus 12 meters. It's unimaginably small.
Now, class, I want you to carefully observe these elements from the second period of your textbook. If we arrange them from left to right, starting all the way from lithium over to oxygen, what exactly do you notice? Take a look. Lithium has a radius of 152 picometers, but by the time we travel across to oxygen, it's actually shrunk down to just 66 picometers. The radius clearly goes on decreasing as we move from left to right. But why does this happen? Let's break down the complex why behind this period trend step by step. Step 1. While we're going from left to right within a period, the atomic number increases by exactly 1 unit at a time. Step 2. This means the positive charge on the center nucleus is getting stronger. Step 3, however, here's the catch. The additional electron gets added into the exact same outermost shell. Step 4. So because that positive nuclear charge in the center is getting stronger, but the distance to the shell hasn't changed at all, those electrons are being pulled towards the nucleus with a much, much greater force. And finally, step 5, due to this strong inward pull, the overall atomic size just shrinks down. Now let's do a quick comparison. Across a period from left to right, atomic size decreases because of that increased nuclear pull on the same shell, just like we discussed. But what happens when we go down a group from top to bottom? The atomic size actually increases. No way, right? But think about it. Why? Because while going down a group, a completely new shell gets added every single time. So the physical distance between the outermost electron and the nucleus goes on increasing. This massive increase in distance completely outweighs any extra positive charge in the nucleus, making the whole atom larger. Moving smoothly on to Section 2, metallic and non-metallic character. Let's shift our focus to how these elements actually behave chemically based on where they sit. Notice that bold zigzag line separating the elements? It's such a brilliant visual for understanding chemical properties. Your metallic elements, like sodium and magnesium, sit comfortably over on the left side of this line. Then your non-metallic elements, things like sulfur and chlorine, sit way over on the right. And right smack on the border itself, that's where we find the metalloids, like silicon. Okay, let's get some formal definitions dictated into your notes. What actually makes a metal, chemically speaking? It's electropositivity. This is simply the tendency of a metal atom to form a positively charged ion, a cation, by giving up or losing its valence electrons. On the flip side, nonmetals display electronegativity. This is the tendency of a nonmetal atom to form a negatively charged ion, an anion, by accepting outside electrons right into its valence shell. Remember, at the end of the day, both are just trying to achieve a nice, stable, noble gas configuration. Metals want to lose, nonmetals want to gain. All right, Section 3, understanding the underlying causes. We know the what. Now we're going to connect that atomic size we just learned about to these characteristics to truly understand the why. Here's a brilliant question straight from the Use Your Brainpower section of your text. I'm posing this directly to the class right now. Why does the tendency of an atom to lose electrons, meaning its metallic character, increase while going down a group? Think back to what we just covered about atomic size increasing down a group. Let's walk through the logic together, shall we? Step 1. As we move down a group, remember, a completely new shell gets added. Step 2.
Because of this brand new shell, the distance between that positive nucleus and the outermost valence electrons increases quite significantly. Step 3. This results in lowering the effective nuclear charge that those outer electrons actually feel. Step 4. Therefore, the attractive force holding onto those valence electrons decreases. Step 5. Because they're being held so loosely by the nucleus, the tendency of the atom to just lose those electrons increases, and hence, metallic character increases as you go down a group. Makes perfect sense, right? Now, class, pay close attention here. I'm reading an always remember rule, and I expect you to literally underline this in your textbooks right now, as it is absolutely crucial for your board exams. Quote, while going downwards in any group, electropositivity of elements goes on increasing while their electronegativity goes on decreasing. And while going from left to right in any period, the electronegativity of elements goes on increasing while their electropositivity goes on decreasing. Please memorize this golden rule. Let's move to section 4, halogen and alkaline families. We're going to apply these broad trends we just learned to observe specific gradations within two very important chemical families. First up, I really want to highlight the halogen family, which is group 17. Look at this fascinating gradation in their physical states as we travel downwards. At the very top, fluorine and chlorine are both gases, but as you move down the group, bromine actually becomes a liquid, and if you keep going down to the bottom, iodine is literally a solid. This physical shift is a perfect illustration of how properties change systematically as you move down a group. Similarly, let's observe the alkaline earth metals over in group 2. Here we see a clear gradation in chemical reactivity. At the very top, beryllium doesn't react with water at all. Moving down, magnesium's a bit more reactive, it reacts with steam. But continue downwards to calcium, strontium, and barium. These elements react with normal water right at room temperature, and the rate of that reaction goes on increasing the further down you go. This beautifully proves what we just learned. Electropositivity, and therefore reactivity for metals, increases as you move down a group. And finally, section 5, solving chapter exercises. It's time to put all our newly acquired knowledge to the test. Keep your pens ready. Let's focus our attention on question 2 from your textbook exercises. Specifically, we'll look at sub-question A. I'll read the question out clearly for the class. The number of electrons in the outermost shell of alkali metals is, and your options are 1, 2, 3, or 7. Now, class, I want you to deduce the answer based entirely on the group number of alkali metals that we discussed in our previous sessions. Remember, they sit right in group 1, correct? Yes, the correct answer is enthusiastically option 1. The answer is 1. Always remember, group 1 elements, the alkali metals, always have exactly one valence electron in their outermost shell. That's literally what defines their group. Excellent work, everyone. Now let's take a look at question 5. This is going to set up your homework assignment for today. To conclude today's class, I'm assigning these specific parts of question 5 as your homework. Please write this down. Based on the modern periodic table, you need to identify and write the name and the symbol for the atom having the smallest size and the atom that is the most electronegative. I highly encourage you to review your notes from today on periodic trends in atomic size and nonmetallic character to find the exact answers. And as you're doing that, I want you to ask yourself this. Isn't it absolutely incredible how the simple addition of a single invisible electron can entirely change whether an element behaves as a life-giving gas or a solid, highly reactive metal? The universe is built on these tiny, perfect patterns. Study well, complete your homework, and I will see you all in the next chapter.